This is an introduction into elimination reactions, followed by a detailed examination of reactions that proceed through an E2 reaction mechanism. An elimination reaction involves elimination of a small molecule from organic substrate. Typically, that means elimination of an electrophile and a nucleophile, which then combine to give a small molecule as byproduct, and organic product is unsaturated organic compound. So a compound contains a pi bond. So a new pi bond is formed as a result of elimination reaction. So product is typically an alkene or an alkyne. Typical elimination is beta elimination. According to trivial nomenclature, carbon atom that is attached to the leaving group or that is bearing a leaving group, in this case halogen atom, is labeled or indicated as alpha carbon atom. Any atom attached to alpha carbon is beta carbon, and then any attached to beta is gamma, and so on. We can have delta and so on. So elimination from alpha and beta carbon atoms gives a pi bond and is called beta elimination. Besides beta elimination, it's possible to have alpha elimination. That would be an elimination of two groups from alpha carbon. We could have gamma elimination, which means elimination from alpha and gamma carbons. That would give three-membered ring. Or delta elimination from alpha and delta carbons. That would give four-membered ring, and so on. Typical eliminations, traditional eliminations, are considered to be beta eliminations, and if we talk about elimination, we mean beta elimination. So in this chapter, we will be looking only at beta elimination reactions. A beta elimination reaction frequently competes with substitution, and that's because reagent for an elimination reaction is a base. And a base is frequently a nucleophile. And so for that reason, reaction could be either substitution or elimination. The outcome will depend on the nature of the reagent and on the reaction conditions. When we are considering reaction mechanism of elimination reactions, the mechanism of beta elimination is actually common to all of the different elimination types. Different reaction mechanisms differ in timing, not in the individual steps. And so general reaction mechanism involves removal of proton from beta carbon by a base, formation of carbon-carbon pi bond, and breaking of carbon leaving group bond. And there are three general mechanisms for polar elimination reaction. So those would be E1, unimolecular elimination, E2, bimolecular elimination, and E1CB. CB stands for conjugate base. So it's conjugate base unimolecular elimination. And we'll actually look at these mechanisms in reverse order. First E1CB, then E2, and finally E1. Here are the three reaction mechanisms. E1 mechanism involves initial loss of the leaving group to give the intermediate carbocation. So that's the first step. And in the second step, beta proton is removed by a base to give the final product alkene. E2 mechanism is a concerted reaction mechanism. There are no intermediates. Instead, all the bond breaking and bond formation occurs in the transition state. So in the transition state, base donates electron pair to form a bond with proton, beta proton. That causes carbon-proton bond to break, and that electron pair flows to form carbon-carbon pi bond, which will cause carbon leaving group to break. All these processes occur simultaneously, and of course, as before, product is corresponding alkene. Finally, E1CB, so conjugate base unimolecular elimination, occurs in such a way that base first removes beta proton. That gives the intermediate carbanion as initial intermediate. And then that free electron pair from carbanion forms carbon-carbon pi bond, and that forces carbon leaving group bond to break in the second step. And again, product is corresponding alkene. As you can see, all three mechanisms involve same processes, same bonds are broken and formed. The only difference is in the timing of the individual steps. E1CB mechanism is somewhat less common elimination mechanism. It's less common than E1 or E2. Nonetheless, it does occur, and we will encounter it in Organic 2 course. So E1CB mechanism In the first step involves loss of proton to give so base removes the proton, and that gives the intermediate carbanion. That intermediate carbanion then forms or is converted into the final product. Free electron pair from carbanion flows to form carbon-carbon pi bond, which causes simultaneous breaking of carbon-leaving group bond. And so the final product is corresponding alkene. Or it may be alkyne, as you will see in a minute. So here are a couple of examples. For E1CB mechanism to operate, there must be acidic hydrogen, or specifically beta hydrogen must be an acidic hydrogen. Hydrogen is acidic if there is neighboring electron withdrawing group. So carbonyl group is typical neighboring electron withdrawing group that makes hydrogen acidic. And so in the first example, that hydrogen is acidic due to the presence of carbonyl group. So base removes that hydrogen, and then in the second step, chloride leaves as an ion, and so product is an alkene. In the second example, we have trichloroethene as the substrate. In this case, proton is acidic because of the presence of 3 electron withdrawing substituents, 3 chlorine atoms. And so for that reason, proton can be easily removed by a base such as hydroxide, and then a chlorine is removed from the neighboring carbon. In this case, product is corresponding alkyne. An E2 reaction mechanism is a bimolecular elimination, which means that reaction rate depends on the concentration of organic substrate and reagent, a base. So here is an example, elimination of bromoethane with hydroxide, like sodium hydroxide. Product is ethene, and byproduct is water and bromide anion. If this was sodium hydroxide, then product would be sodium bromide. Reaction rate depends on the rate constant and concentration of substrate and the base. Or in this specific example, reaction rate depends on the rate constant and concentration of bromoethane and hydroxide anion. Here is the reaction mechanism. So reaction is a concerted reaction. There are no intermediates, it's single-step reaction. So hydroxide base donates free electron pair to form a bond with proton, with hydrogen. So oxygen-hydrogen bond is formed. As that bond is being formed, of course, hydrogen cannot form 2 bonds. So, or hydrogen cannot have 2 bonds. So carbon-hydrogen bond is simultaneously being broken. So that electron pair flows to form carbon-carbon pi bond. And since alpha carbon of this compound, of course, cannot form 5 bonds or have 5 bonds, then simultaneously with formation of carbon-carbon pi bond, carbon-bromine bond is broken. And so this is transition state. As you can see in transition state, all the bonds are partially broken and partially formed, and you can see how partial charges alternate, starting with partial negative charge on oxygen and then partial negative charge on hydrogen, and so on, all the way to partial negative charge on bromine. Finally, when bond breaking and bond formation process is over, we have final products. We have ethene, water, and bromide anion. And here is reaction diagram. You can see from this reaction diagram that reaction is actually endothermic. Here are some examples. So, for example, elimination of iodoethane with tertiary butoxide, like potassium tertiary butoxide. Reaction works very well. Tertiary butoxide is frequently used as a base because it's non-nucleophilic. So there is no competition with substitution reactions. Of course, we can use ordinary base such as methoxide. So elimination of 2-bromopropane with methoxide gives propene as a product. When there is possibility for formation of regio and stereoisomers, we often get a mixture. So elimination from 2-chlorobutane with butoxide gives both cis and trans isomers of 2-butene and 1-butene. So 1 and 2 butenes are regioisomers, so we get 2 regioisomers, and cis and trans 2 butenes are 2 stereoisomers. We get both of them. So we get mixture of all 3 compounds. And sometimes we get even more complex mixtures, as in this case of 3-bromohexane when we get 2 and 3 hexanes and cis and trans isomers of each, so we get 4 products. So as you can see, sometimes reaction is not that useful because we tend to get rather complex mixtures. Finally, one convention point. This wavy bond that you have seen that I'm using here means that either stereochemistry, in this case cis-trans stereochemistry, is not known, or that we have a mixture of stereoisomers. In this case, we have a mixture. So we can use it for either way. Even if we don't know, if we have one product, but we don't know whether it's cis or trans, we can use these wavy bonds to simply state that we don't know what we have. Or if we know that we have a mixture, then we can use wavy lines to indicate that we have a mixture. That's a little bit unfortunate that it's used for both when we don't know or when we have a mixture. So you have to draw a conclusion from a context what wavy bond indicates, whether it indicates a mixture or that we don't know stereochemistry. And another example is in case of chiral compounds, in this case 2-butanol. So now either we have a mixture of 2 enantiomers or we don't know which enantiomer we have. And from the context you would draw a conclusion. As shown like this, you actually wouldn't know. You wouldn't know whether it's a mixture or whether we have, or whether we don't know which enantiomer we have. Reaction rate of an E2 elimination reaction is affected by the degree of substitution of substrate, but maybe not in the way one would expect. And for that we should consider transition state. In the transition state, reagent approaches proton on the beta carbon. It does not approach carbon that is bearing the leaving group. So for that reason, steric hindrance is actually not very important. The fact that this is tertiary alkyl bromide is not really important because reagent, in this case, base does not approach tertiary carbon. The base interacts with hydrogen on the beta carbon. So steric hindrance does not play a role. It's electronic effects that play a role. So you can see that in this case, partial charges are developed. So oxygen of the base carries partial negative charge in the transition state, proton partial positive charge, then beta carbon partial negative charge, alpha carbon partial positive charge, and final leaving group partial negative charge. What is important is that alpha carbon that is bearing the leaving group, is developing partial positive charge. So that carbon resembles carbocation, and stability of transition state will actually depend on stability of that developing positive charge, that carbocation-like species. And that means that transition state where carbon is tertiary, carbon that is developing partial positive charge is tertiary, so carbon that is bearing the leaving group is tertiary, is going to be lower energy, more stable transition state compared to one where such carbon is secondary. As you know, hyperconjugation stabilizes, hyperconjugation by neighboring substrates, neighboring substituents, stabilizes developing positive charge on the carbon. So tertiary substrate is more stable compared to secondary, or transition state involving tertiary substrate is more stable compared to one involving secondary substrate, and that one in turn is more stable compared to one involving primary substrate. And for that reason, order of reactivity is maybe somewhat unexpected. Tertiary substrates react the fastest in E2 eliminations, then secondary and finally primary. And that's because electronic effects play a role. So stability of transition state depends on electronic effects and not on steric effects. So if we compare E2 elimination with SN2 elimination, actually the order of reactivity is the opposite. And that's because in SN2 elimination, it was steric factors that were the important factors in the transition state and were affecting the stability of the transition state. Here, it's electronic factors, and for that reason, the reactivity order is opposite. Regioselectivity of an E2 elimination can follow either Zaitsev or Hofmann pathway. First, we look at Zaitsev elimination, that's predominant pathway. Zaitsev elimination is elimination that follows what we call Zaitsev rule. So Zaitsev rule states that hydrogen is removed from the beta carbon that is bonded to the fewest hydrogens. Just like Markovnikov rule, this is an empirical rule that Zaitsev formulated in 19th century before mechanisms were known. So simply this was formulated on study of large number of examples, and then from that study empirical rule was formulated. There is some doubt whether it was Zaitsev actually who did the work and who came up with this rule, but nonetheless he was the one who published the work and rule is attributed to him. So here is one example of application of Zaitsev rule. Elimination of 2-bromobutane with, let's say, sodium ethoxide as a base could give 2-butene and 1-butene as 2 regioisomers. So carbons 1 and 3 are beta carbons in this case. Carbon 3 is CH2 is methylene group, and it has 2 hydrogens. Carbon 1 is methyl group, it has 3 hydrogens, so carbon 3 has fewer hydrogens, has only 2. So predominantly elimination will occur from carbon 3, and so major product as expected is 2-butene. And here is the reason why. We should look at transition state because of course this is an E2 elimination. So transition state that leads to formation of more substitute double bond is more stable, lower energy transition state, because more substitute double bond is more stable compared to less substitute due to hyperconjugation, electron delocalization from the substituents. So simply we are looking at developing double bond. So developing double bond will result in lower energy transition state if it's more substitute. So less substitute double bond, obviously higher energy transition state. So this is a kinetically controlled process, and it has to do simply with formation of more stable, more substitute double bond. And here is the energy diagram. As you can see, the eliminations, we have seen that before, are endothermic reactions, and transition states are product-like transition states, late transition states. So transition state, energy of transition state, relative energies resemble energies of the products. So since more stable double bond is lower in energy compared to less stable, less substitute double bond, so more substitute, in this case disubstitute double bond, is lower energy compared to monosubstitute double bond. That means that also transition state that leads to formation of more substitute double bond is lower energy compared to transition state that leads to formation of less substitute double bond. And so formation of more substitute double bond is both kinetically and thermodynamically favored. This process is kinetically controlled. Alternative elimination pathway is Hofmann elimination. And if Hofmann elimination, of course, less substitute alkene is formed. Hofmann elimination pathway is favored if there is poor leaving group, such as fluoride ion, and this is the first time that we are encountering fluoride as a leaving group. So it could be a leaving group in E2 eliminations, and it favors Hofmann pathway. Or if there is large sterically hindered base, or if there is steric hindrance in the substrate. So the last two are related. Basically, if there is steric hindrance present, either in the substrate or the base, or both, Hofmann elimination is favored, or alternatively, if there is poor leaving group, such as fluoride, that also favors Hofmann elimination. Here is why. If we consider transition state, and we consider first case, so poor leaving group, such as fluoride anion. So what happens in the transition state? We have charge separation. So we have charges alternating, starting with negative charge, partial negative charge on the base, partial positive on hydrogen, and then we have developing partial negative charge on beta carbon, partial positive charge on alpha carbon, and partial negative charge on the leaving group. But in this case, leaving group is poor leaving group. So what happens is that base, methoxide, starts donating in the transition state, or in transition state is donating electron density to the substrate. So basically you can understand it's pushing electron density, pushing its electrons to the substrate. But at the same time, we have poor leaving group, fluoride. And so as a poor leaving group, fluoride actually won't leave that easily, and it's not leaving. And the end result is that in the transition state, negative charge backs up in the middle. It backs up on the beta carbon. And so carbon ends up with excess negative charge. So stability of the transition state is going to depend on how well this beta carbon handles the negative charge. Well, so this negatively charged carbon resembles, in terms of stability, carbanion. We did not cover stability of carbanions so far, but you can guess that stability of carbanions is going to be opposite from that of stability of carbocations. So if order of stability of carbocations was tertiary the most stable, then secondary, then primary, and finally methyl least stable, order of stability of carbanions is going to be the opposite. Methyl is the most stable, then primary, then secondary, and then tertiary. Because electron donation through hyperconjugation means electron donation in case of carbanion to species that already has excess electron density, excess negative charge. And this would be simply donating even more negative charge to it, and that means making it even more unstable or less stable. So for that reason, the fewer substituents we have on carbanion, the better, the more stable it is. And so for that reason, in this case, carbanion-like species, carbon with developing negative charge, is going to be more stable if it's less substituted. And that's, in this case, primary, as opposed to situation on the left where it's less stable, it's secondary. So with fluoride as a leaving group, or poor leaving group in general, Hofmann elimination or formation of less substitute alkene is preferred. And the reason is electronic. And here we can summarize stability of carbanions. So as you can see, tertiary carbanion is the least stable because it has 3 electron donating groups, and they destabilize negative charge by donating even more electron density to it. Then secondary, finally primary, and the most stable is methyl because it has no substituents, nothing to donate negative or to donate electron density to negative charge. Some examples of Hofmann elimination, of course, involve elimination of alkyl fluorides. As you can see, it's only preferred, formation of less substitute alkene is only preferred, so it's 70-30 in this case. And same goes for Zaitsev elimination. In case of Zaitsev elimination, formation of more substitute alkene is only preferred. We get 80-20 or something like that. And also Hofmann elimination operates in case of steric hindrance. If there is steric hindrance in substrate or base, or both in this case. Because then, because of the steric hindrance, less hindered proton is removed. And less hindered proton is, of course, on less substitute carbon. And so in this case, it's steric reasons why Hofmann elimination operates. So Hofmann elimination may operate either for electronic reasons, if there is poor leaving group like fluoride, or for steric reasons, if we have a sterically hindered base or sterically hindered substrate like tertiary, or both, hindered base and hindered substrate. In summary, Zaitsev elimination gives a more stable alkene, while Hofmann elimination gives the alkene that forms faster. Now, while that would appear from that summary that Zaitsev elimination is thermodynamically favored and Hofmann is kinetically, that's not true. Both are kinetically controlled. But Zaitsev proceeds through low energy transition state, and that's why lower energy transition state in Zaitsev elimination also leads to formation of more stable alkene. So both Hofmann and Zaitsev elimination proceed through lower energy transition states, and they are both kinetically controlled reactions. This completes our examination of E2 eliminations, and next we are going to look at E1 elimination reactions.